Right, so we've got a worked solution for a vector geometry problem. This is one of the sort of harder type of problems that you're going to get usually at A level. But we do also see this problem at CIE at additional maths. Um, okay, so let's just have a look. Um, the diagram shows a triangle OAB such that OA equals A and OB equals B. Yep, that's our A marked on here. Here, uh, P on A such that OP equals 3/4 of OA. So that means that that ratio is 3 to 1. Q is the midpoint of AB. Doesn't quite look it there, but these diagrams are always kind of not to scale. So that's the midpoint of AB. And OB is extended to R to meet the extension of of PQ. Um, um, there, that's right. Okay, so find in terms of A and B. First of all, find AB. All right, so this is very straightforward. This first part. Um, AB, well, it's like to write it like this. What we're doing is we're finding another journey, if you like, from A to B, and we're going to go via O. So we can write this AB as AO plus OB. I always like to to start off with this line segment format and then develop this expression until we know all the constituent parts. Right, okay, well, there's no more work to be done on this particular one because AO we know to be is minus A and OB is B. So um, minus A plus B, B minus A. Okay, so that's part A. B, find PQ. Right, so similar thing, PO to OB to BQ is the same journey as PQ, isn't it? From P to Q via O there and via B. So we're going, we want this vector down here, but if we look to go down this route, then we've got the same vector. So let's have a look. Yeah, we know that PO, I mean, essentially it's going to be OP is 3/4 of OA, so PO is minus 3/4 of OA, so that's all right. We're all good with that. OB, we know it's B. BQ. Right, well, this is Q is halfway along there, so BQ is going to be half of BA. Right. Um, we know AB already. Okay, so we got PO plus OB plus half of BA, so that's going to be minus 3/4 A. That's from PO plus B, and then minus because obviously we're going in the opposite direction to AB. We're going from B to A, but we're just going halfway of that journey to Q. So that's minus half of B minus A. Okay, we simplify that, we get this expression here, minus quarter A plus a half B. Okay, so right now this is where it gets interesting. We've got to find QR. Right, so given that we don't know what this is and we don't know what that is, um, can we use either of those routes or either of those vectors on our route? Well, the answer is kind of no, really, because neither of them is going to give us a solution. We are told, though, that well, we could actually kind of define some scalars here which gave this ratio, but they've done it for us here. It's given that NPQ equals QR. So put in there. So that's the ratio of PQ to QR there. And also BR equals KB. All right, so that gives us the ratio of this to this in effect. Um, okay, we could define this slightly differently, couldn't we? We could actually say that, oh, well, certainly in this case, we could actually say that PQ equals NQR, to N, invert it, so it's just a question of definition, really. Um, So, but that's what they've given us to use. So we're obviously just going to stick with that. So, right now, so the solution to this basically hinges on the fact that A and B are linearly independent. So they might not be perpendicular, which is something we're kind of used to in other forms of vector problems, particularly say in mechanics. Um, but in general, the linear independence of A and B, it basically means that one isn't a scalar multiple of the other. Um, their linear independence means that we can define any point or any vector in this plane, the plane being the paper, in terms of A and B. Right. Okay. So that's what we've got. So that is the aim. And if we do that, what we need to note is that if we have two vectors um, which are linear multiples of A and B, then we can equate the A parts and equate the B parts. All right. A little bit like we would do if they were perpendicular, but we don't need the condition that it is perpendicular. All right, so let's just see what that means in a moment. So QR. QR is equal to NPQ. All right, that's just what they've told us there. And PQ is what we've calculated here. So it's that. So that is what we've got for QR. It's in terms of N. Okay. All right. Now, if we, and what we've used to do that is we have used for QR, we've just used this route basically, haven't we? But we could actually choose a different route. We could do this. We will get the same route. We'll get the same vector. We're still going to get QR even if we go via B. So if we write QR equals QB plus BR, all right. Okay. Then QB equals QB plus BR. So QB is going to be half of AB. Yep. Okay, so this ratio is 1 to 1. So half of AB plus BR. Well, BR is equal to KB. So that's what we've got there. And if we substitute our AB in there for that, we get this expression. Okay, so now we've got two expressions for QR. All right, that one and that one. And because of the linear independence, we can actually equate the A part. So if we do that, so if we take the, let's just wind down a little bit. So yeah, so those two are equal. Those are two expressions of QR. So if we take the A part, this bit equals that bit. There we go. And that's going to give us n equals -2. So that's just an equation in n, isn't it? And then now we know n. We've got that equals that. So if we just strip that b out, there half n equals a half plus k. Then given that n is equal to 2, then basically that just works out. You can work that out for yourself. If you're not sure, just pause the video and just have a look for yourself. But that gives us k equals a half. So yeah, so we found QR in terms of both expressions there. That's part C. That's part D. And then in E, we found found N and K. It doesn't actually say, therefore, what is QR, but QR, therefore, just by using those values of N or K. I think I've actually used that one there. Then we get this. QR equals B minus half A. Right. So that's not too bad. There are forms of these questions that are a bit more difficult. At least this one we're given some what's called scaffolding because they've actually given us these these ratios. So this kind of gives us a bit of a helping hand. But on other problems, you may just be asked out of all this to find uh, vector QR, in which case you would have to define these ratios for yourself and observe that we can actually, by doing this, we can actually find two sort of different expressions for QR. Okay, so that is that. This problem is my courtesy of Save My Exams, by the way. So you could go on there and have a look at the if you've got an account, go on and have a look at the solution on Save My Exams. But it's essentially going to be like this. One other thing I might just say is that when we look at a problem like this, how do we know we can actually solve it? Are we given enough information? Um, you know, not necessarily. It depends on the problem. But if we look what we are given here, okay, we've got how many line segments have we got? We've got one, two, three, four, five, one, two, count again. One, two, three, four, five, six, seven, eight. 8 line segments in there when we break it right down into sort of constituent parts. How much information are we given? Well, we're given A, we're given B, we're given two ratios here. Okay, that's 4 pieces of information. And then we've got the collinearity. So this is collinear with that, and that is collinear with that. And this is collinear with that, three collinearity things. So we've got 7 pieces of information relating to 8 line segments. All right. So now I'm not going to go into any more detail than that on this video, but watch out for another video on this subject, which will actually kind of analyzes this sort of idea as to how many pieces of information do you need in order to solve, and in what form uh, can that information be. All right, so I'll sow that idea in your mind, and hopefully that has been useful. So thanks for watching.